Hello. So we've been working a little bit with a variety of conjugate priors, including the beta for the binomial. But really, you just multiply the likelihood by the prior to get the posterior distribution up to proportionality. So I can pretty much do any prior I want. So I wrote a little program yesterday for entertainment value. What this does is it's going to allow me to freehand write a prior. So I will do that. Freehand write a prior. And so I can say, I don't think it's very likely to be 0. Yeah, I think 2. 0.2 is highly likely. Oh, I don't like 0.5. I'm going to have it low, very, very low for 0.5. Then I'm going to go up as we get up to probably 1, and then I'll see what that looks like. I hit this. Okay, this is the prior I just picked, and that one goes a little negative, which it's actually just going to cut it off at 0. So it's going to make values impossible in this little gap. Now let's say I didn't do much coin tossing. So I tossed the coin 4 times and got 2 heads. Okay, that's going to compute it's going to, based on that, compute the likelihood based on the binomial, which is proportional to a beta. It's going to multiply it by the spline. This actually fits splines to those locations I clicked on. It's going to multiply them together to get a posterior distribution and then plot it. So let's see what that looks like. Oh, look at that. Dropping down like that completely messed. There's my posterior distribution. Since I said it couldn't be around there in my prior, it's going to be really, really low. We don't have much data either. So that's what we get for a posterior distribution. Turns out I can even simulate values of my parameter theta, the probability from that, pretty easily. What I'm going to do is rejection sampling. So rejection sampling is I'm going to uniformly generate points in the x direction and the y direction. And if they're under the curve, I keep them. If not, I throw them out. And then I count how many points are left at each x value. And where it's high, there will be a lot. And where it's low, there will be not many. And that'll give me a simulation of independent observations from that distribution. So, and then I'm going to do a histogram of those and compute their mean and standard deviation. Let's see this. Okay, look at that. Nothing happened around there. So here's the distribution, simulated data, and it had a mean of 0.45 and a standard deviation of 0.23. Of course, this is very dominated by a prior. So let me do something a little bit different. I'll do these again, do a new prior. Let's do one that says, okay, there's very little chance that when you toss a coin, you'll get 0 probability of heads. That'd be a weird coin. But I'll have it go up pretty steeply. And then at about 0.2, I'm going to have it be very, very flat. How's that for a nice prior? And then it'll go down again and say, I don't think there's much chance of the coin always coming up heads. And that's the prior distribution I came up with. Let's put more data. Let's say you tossed the coin 40 times and you had 22 heads. You'll notice this is a very flat prior in the middle part. So since our data is pretty close to 50% and there's lots of data, it's going to completely dominate the prior. So the posterior is going to look nice. Let's see. Oh, look at that. That's the posterior distribution. Finally, I'll simulate it and look at its mean and variance. There it is. That's a nice looking distribution. And it has mean 0.54 and variance 0.076. Wonder how close that is to the actual proportion. 22 over 40 is 0.55. See, it barely moved the mean. All right. And I'll put this code in Blackboard so you can see it if you want. Bye.